Hello everyone, my name is Patrick. I'm very excited to be here to introduce our work, HIVE, which is a hardware-assisted isolated execution environment for eBPF on AArch64. So I will discuss about these 6 parts. The first part is, what is eBPF? eBPF can be used to safely extend the kernel without changing kernel code or loading kernel modules. The user process can use the BPF syscall to load the BPF program into the kernel, and the kernel will use its verifier to ensure that the program causes no harm to the kernel. After the program is approved, the kernel will use the JIT compiler to emit native instructions for the program, and the program will be hooked at the location that is specified by the program. And then the program runs in an event-driven manner. The kernel provides an execution environment for eBPF. It includes 11 registers, which are mapped into native registers, and the kernel provides a program context object. The program can also declare map structure, which are key-value-based memory regions. The kernel also provides some hyperfunctions to expand the functionality of the program. The program also has its own stack, which is located on the top of the kernel stack when the program is running. So the verifier serves as the security barrier between eBPF and the kernel. We analyzed all security checks and summarized them into 20 security properties. The BPF check function is the entry point of the verifier, and the do check function contains most of the security checks. Basically, it maintains a state machine, which records the type and the range of all the registers under all possible execution paths. Whenever an instruction is encountered, it will perform security checks based on the semantic of the instruction and all operand states. For example, for the load instruction, it will check if the source register is initialized and must be pointer type. Then it ensures the memory access is inbound. If the instruction passes the check, the state machine will be updated. We can see these security properties are at the implementation level. So based on them, we summarized the security goals at the design level, corresponding to the kernel's integrity, confidentiality, and availability. For the first goal, BPF program can only access its own memory with the right permission. For the second goal, the information leakage should be prevented, including kernel layout information, uninitialized information, and also the spectral attack should be prevented. For the third goal, the DOS attacks should be prevented because the permission is disabled when the program is running, and the exception handling is not supported in eBPF. However, the verification-based method has become the bottleneck of eBPF. The first dilemma is the correctness dilemma, which means unsafe programs can pass the verification. We analyzed all BPF-related CVEs in the last decade. We can see the verifier contributes the most of the CVEs. The second dilemma is the capability dilemma, which means safe but complex program cannot pass the verification. This is because the verifier needs to traverse all possible execution paths, which brings the state explosion problem for these complex programs. So our goal is to address these dilemmas and provide the same security goals as the verifier. So our key insight is that the BPF program can be viewed as kernel mode applications. So we can learn from the isolation of user applications. The user mode application runs at EL0, so it cannot access kernel memory because these kernel memory pages are privileged. Each user application runs in its own independent address space, so they have no kernel layout information. And last, the hardware provides the crash isolation for the user process. So based on the user application design, our design is to deprivilege BPF programs. We leverage the unprivileged load store feature in AArch64 to provide the EL-based memory isolation, because these LSU instructions are treated as at EL0, no matter which EL they are running on. After that, we add an independent BPF space for the BPF data to eliminate kernel layout information. And last, we provide the exception rollback mechanism for eBPF. However, the above design faces several challenges. All these challenges stem from the fact that BPF programs are highly coupled to the kernel. The first BPF objects require object-grained isolation because metadata, like pointers, is embedded in BPF objects, and these metadata cannot be accessed. But the EL-based memory isolation cannot provide such subplate protection. The second challenge is that kernel objects need to be accessed securely, because BPF programs can directly access specific fields of kernel objects, but the EL-based memory isolation prevents such legal access and cannot provide such fine-grained protection. Also, there are some other challenges. So our detailed design is to address these challenges. We take the stack as the example. When the program is running, the stack contains many BPF inaccessible data, including the kernel's local variables, the return address, and some cohesive registers that are spilled on the stack. So our solution is to compartment the BPF stack from the kernel stack by switching the BPF stack pointer to a specific memory region. Similarly, the metadata of other BPF objects are also separated. Then we map the BPF data into the BPF space with unprivileged permission. Based on that, the solution to kernel space is set by transforming all memory access instructions in the program into SU form in the JIT stage of the eBPF. However, the program may access the user space because they're using their LSU instructions, and the vice versa. So we use the E0PD feature to isolate the user space and the BPF space. For the second security goal, the BPF space has no kernel layout information, and it is initialized during the program loading time. And all BPF used registers are cleared when the hyperfunction returns. For the spectral attack, the LSU transforms the spectral attack into the meltdown attack. And the CSV3 hardware patch forbids the speculatively loaded data with a permission fault to be used to form an address. So we can prevent the spectral attack without any efforts. For the third security goal, we provide the exception capture to prevent kernel crash, and we provide the execution timing to prevent execution without terminating. The above is half of our design. The other half is to handle these kernel pointers in the BPF program. Since these pointers point to the kernel space, we need a new solution for the first and the second security goals. Our insight is that these pointers cannot be modified, and the dereference points must be exclusive because of the functionality requirements of eBPF. So we use the ARM pointer authentication to ensure the pointer integrity and the type safety. Due to the BPF accessible kernel objects are in privileged page, we need to use the regular load store instructions. So the following questions are: how do we identify memory access to kernel objects? And how do we prevent attacks against the PA, like the replace attack, the spectral attack? And how do we prevent the signed pointers from being leaked? Due to the time limitation, I cannot introduce the detail. Please read the paper if you are interested. So our evaluation contains 3 parts. We first conducted attacks to the security properties, and these attacks are mitigated by us. Second, we load over 100 BPF programs into the kernel and run some real-world applications like Nginx and Redis to measure the throughput slowdown of vanilla eBPF and HIVE. You can see HIVE is very efficient. It brings less than 5% throughput slowdown. At last, we perform the complexity evaluation. Because as the kernel developer claimed, the goal of eBPF is to replace kernel modules. But now no kernel module can be replaced because of the capability issue. We compiled 10 kernel modules into BPF programs, and all of them are rejected by the verifier because they have like unbounded loops or too many branches. Then we run them successfully in HIVE. So let me conclude my talk. The verification-based method has become the bottleneck of eBPF. We provide a hardware-backed isolation environment. It has a deprivileged and a decoupled BPF environment, and we provide a special design for accessing kernel objects. The evaluation results show that HIVE can provide the same security guarantees with low runtime overhead, and it also addressed the capability issue. Now BPF programs can be as complex as they want. Okay, thank you.